This review is of chapters 19 through 22 on inference in general and in particular inference for proportions. So the first kind of inference that we learned was constructing a confidence interval. Now when you calculate a statistic from a sample, like a proportion, you often do so to estimate the true population parameter. The sample result is called a point estimator or point estimate of the true value in the population. Now, because we know there's sampling variability, we realize that the population parameter is probably not exactly equal to our sample result, so we want to say how accurate the estimate is. We want to be able to quantify that a little bit. We use what we learned in Chapter 18 about sampling distributions for means and proportions, and we know that they follow a normal distribution if certain conditions are met, and that those normal distributions are centered at the true population parameter. So if we can reach out a certain number of standard errors from this sample result that we got, we can quantify how close the estimate tends to be to the population true value in repeated random sampling. And how the number of standard errors that we reach out, how far we're reaching out on either side, that's called a margin of error. Now, a confidence level, like 95% confidence, that tells the success rate of capturing the true population parameter in that interval that you created, okay, if you were to do it repeatedly over and over and over again. Okay, so usually we really only create one interval, we only reach out once, but the idea is that let's say you reached out 1,000,000 times. If you have a 95% confidence level, 95% of those million intervals would contain the true population proportion somewhere within them. Okay, that's what a confidence level means. Now, how do you interpret confidence level? Again, pay attention to vocabulary. Confidence level versus confidence interval. Level is the percent, and if they ask you to interpret that, you say 95% of all possible samples of this size, n, from this population would result in an interval that captures the true population proportion or mean or whatever, okay? According, may not be 95%. It depends on what confidence level you're doing. Now, if they ask you to interpret the confidence interval, which is the more common thing that they ask for, then that's the statement where you say, we are 95% confident that the interval from blank to blank captures the actual value of the population parameter. But you would state that in context. So I might say, we are 95% confident that the true proportion of U.S. female adults whose favorite color is red is between 15 and 22%, something like that. So we learned how to do a confidence interval and a hypothesis test for one proportion, and we also learned how to do it for comparing two proportions. So first let's talk about one proportion confidence interval. So to create your interval, you take your sample statistic, your p-hat, and you're going to add and subtract to that a margin of error. And margin of error is a z-score, which represents how many standard errors you want to reach out. So it's a z-star times that standard error. So like I'm reaching out 1.96 standard errors, or I'm reaching out 1.64 standard errors. Okay, that z-star, I'll tell you how to calculate that in a minute, but you reach out that many to get a certain percent of that normal model. Okay, remember that this z-star times the standard error, that is called a margin of error, and it's how far you're reaching out from the middle. Okay, on your calculator, that would be one proportion z interval. Again, this standard error we learned in chapter 18 for proportions is the square root of p hat q hat over n. Okay, now finding the critical value z star. How do you do that? Well, you draw or imagine a normal model with whatever confidence level you want shaded, so like 95% shaded, symmetric about the middle. And then you imagine, okay, what's left in the two tails? Well, if I've got 95% shaded, that leaves 5% in the two tails, 2.5 in each because it's symmetric. So the lower one would be at the 2.5 percentile, the upper one would be at the 97.5 percentile. So then you go and look up that percentile in the z table in the back of the book, and you read off the z-score that corresponds with that. Or on your calculator, you can use inverse norm, parentheses, the percent. Okay, so like inverse norm 0.95 or inverse norm 0.025, inverse norm 0.975, whatever percent is appropriate to get that z-score. It's good to memorize the most common z-stars, like 95% is a z-star of 1.96. Okay. Some other questions that come up related to confidence intervals is to find a sample size that would give you a particular margin of error that you want, as well as a particular confidence level that you want. So like, what sample size do I need to have a margin of error of plus or minus 3% with 95% confidence? So basically you write down your margin of error equation. Margin of error equals z star times the standard error, and then you plug in the desired margin of error. So like 3% would be 0.03. You plug in the z star that goes with the confidence level you want, like 1.96 for 95% confidence. If you know a p hat, q hat, because you've done a sample, you can plug those into your square root of p hat, q hat over n. If you don't know them, then you estimate them with 0.5 and 0.5 for both, because that gives you the largest sample size, so you're erring on the side of caution. So square root of 0.5 over n. And then you have to do some algebra and solve that equation for n. Some of you did have some trouble with that algebra, so you might want to read pages 374, 375 for an example to make sure that you could do that if you were to get a question like that. Conditions that you need to check to do inference for proportions. You need to check that it is plausible that your sample results are independent of one another. You need to check that you have random sampling or random assignment. You need to check that your sample is less than 10% of the population, which is related to independence. And you need to check success-fail that NP and NQ are both greater than 10. Now for success-fail, if you're doing the confidence interval, you're checking that NP hat and NQ hat are both greater than 10. But if you're doing a hypothesis test, you're checking P naught and Q naught instead of P hat and Q hat. Okay. How do you do a hypothesis test for one proportion instead of a confidence interval? Well, you start by writing out your hypothesis. Okay, so our null hypothesis is usually H naught colon P equals some hypothesized value, like 0.5. Okay, no hats, because this is a parameter. You're saying I'm hypothesizing that the real value is this, so no P hat, it's P. Your alternate H sub A colon P is either greater than whatever you hypothesized, or it's less than whatever you hypothesized, or it's not equal to whatever you hypothesized. Okay, and that depends on how the question is worded. Then if you wanted to, you can imagine or draw the normal model that represents this. It centers at P, okay, whatever your hypothesized is, and it has a standard deviation of the square root of P naught Q naught over N. Okay, and then you can find the z-score of the sample result you got. So basically you're saying, if this hypothesized model is what is actually true, how unusual is my sample result that I got? That's basically what you're finding out. And you can use the z-table, or you can use normal CDF to find the area of the shaded region. So like this sample result or more extreme, okay? How likely is that? What proportion of the area under the normal model is that? Don't forget that if you're doing a two-tailed test, which is a not equal alternate, that whatever area you found, that was only, one tail, so you need to double it to get your actual p-value. Okay, otherwise you've got a p-value for a one-tailed test only. On your calculator, this would be a one-prop z test. Make sure you report z and p-value, so your test statistic and the proportion shaded on your paper. Okay. Don't forget to define your variables. This should go up in the state part of what you're doing. When stating your test and interval you'll be doing or writing your hypothesis, you should define the variables used in writing those hypotheses so there's no confusion. Beware of writing down whatever your calculator spits out without defining or explaining what those numbers represent. Okay, so if there's a p hat and a p1 and a p naught and all that stuff on your calculator, if you're going to write it down, make sure you tell somebody who's going to read that what that number is, what that stands for. Okay, otherwise don't write it down unless you need to. How do you decide whether to do a one-tailed test or a two-tailed test? It depends on the way the question is worded, right? If the question is worded so that all you want to know is there a difference here, or is this the actual value or not, then that's a two-tailed test. Okay, so you just want to know if the null is true or not. On the other hand, if the question is worded, we have reason to believe that it may actually be greater than this, or is it less than this, then you're looking at a one-tailed alternate, either greater than or less than. Okay, how do you write your conclusion for a hypothesis test? Okay, well you will either use a given alpha level, significance level, or you will choose an alpha level. Usually we defaulted to 0.05. And then you basically compare your p-value, the shaded area, with your alpha level. If the p-value is below alpha, we reject the null. If the p-value is above alpha, we fail to reject the null. So basically we're saying, if this result is below my threshold for how I could consider something to be too rare to believe in my null that I'm going to reject. So if P is low, reject HO, right? And then you write your conclusion as follows. The p-value of blank, like 0.23, is above our alpha level of 0.05. Therefore, we fail to reject the null hypothesis, and we conclude whatever the alternate says in context. Or the p-value of 0.03 is below our alpha level of 0.05. Therefore, we reject the null hypothesis and conclude whatever the alternate says in context. Okay, so if you're failing to reject, you say we conclude whatever the null says in context. If you reject, then you say we're concluding whatever the alternate says in context. Be careful and stick to the terminology, just saying we're concluding this, not that it is this, right? Because we could be wrong. All right. Significance level and confidence level, how are they related? How are alpha and C related? Okay, so if you choose an alpha level of 0.05, for example, 1 minus that gives you the confidence level for a corresponding two-tailed test. So 1 minus 0.05 is 95%. Okay, and that means that if you're doing a two-tailed test with 95% confidence, you'd make exactly the same reject or fail to reject decisions as choosing alpha equals 0.05. Now, if you're doing a one-tailed test, all of that alpha, all of that 0.05 is just in one tail. So instead of your confidence level being 1 minus alpha, it's actually 1 minus 2 alpha. So if I have alpha equals 0.05 and I want to design a confidence interval that would give me the same conclusions of rejecting and fail to reject, then I would use 1 minus 0.1, 1 minus 0.05 times 2 alpha as my level of confidence, so 90% confidence. Okay, now errors. You do have to know which one's which, so you need to come up with some way to remember that a type 1 error is rejecting the null when it really is true. A type 2 error is failing to reject a null that is really false. Okay, the probability of a type 1 error you determine when you set alpha. Alpha is the probability of a type 1 error. So if I say alpha is 0.05, I have a 5% chance of rejecting the null when it really is true. Okay, the probability of a type 2 error is represented by the Greek letter beta, but there's actually a different beta for every specific alternate value you might want to detect. Like, so if my null hypothesis is that p equals 0.3, and so there would be a beta for being able to make the correct decision. If the real value is 0.2, there would be a different beta for being able to detect if the real value is 0.15, making the right decision. You will never have to calculate beta, but you should know that what the probability of a type 2 error is represented by and what it means in general. Okay, the power of a test is 1 minus beta, and you do need to understand what power means. It is the probability or ability to detect a null that is false. Okay, so be prepared to answer questions. What does the power of this test mean? What is a type 1 error here? What would a type 2 error mean? What's the probability of a type 1 error if you do blah, blah, blah? Okay, now if you increase alpha, so if you make alpha equal 0.1 instead of 0.05, which would correspond to lowering your level of confidence, that means you increase the probability of a type 1 error and the power of the test, but you decrease the probability of a type 2 error. Now, increasing sample size can increase the probability of both types of error. Increasing sample size can decrease the probability of both types of error and increase the power of the test. Okay, so increasing sample size in general is a good thing. Now, in reality, you almost never know what type of errors have occurred, if any. You analyze what types of error would be the most damaging and choose your sample size, alpha level, confidence level, and so on accordingly. Make a truth table to help you analyze the risks. So go back in your textbook and look up truth tables to remind yourself how to do all this. And yes, you do need to be able to say, hey, if I want to reduce this probability, this kind of error, I should do this. I should increase alpha, or I should decrease alpha, all those kind of things. Okay. Last thing is, what about those 2 proportion z-test and 2 proportion z-interval? Again, those are named that on your calculator. Everything's the same as what we've just talked about, except for these differences here. When you're checking conditions, you need to check that the 2 groups are independent of each other, not just individuals independent. Check success fail for both groups. The standard error formula is square root of p1q1 over n plus p2q2 over n2, right? Because we have 2 different groups. And the confidence interval is calculated exactly the same way, except instead of a sample value, it's the difference between the 2 groups that you're starting at, and then you're adding or subtracting your margin of error. Your null hypothesis is usually that the difference between the 2 proportions is 0, but not always. And the standard error for hypothesis uses p total and q total instead of p1, q1, or p2 or q2. And that concludes our review of